Let me check if I'm alive. Yeah. Let me check if I'm alive. Yeah. Okay. Hello, 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 hello. Am I audible? Hello, 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 hello. Am I audible? I hope so. I'm audible. Let me check with my second device. Got that. Hello, hello, hello. Hello, folks. Yep. Hello. Which round was it? Education round 190. Should we start? Should we start, folks? So, you folks, this is Devansh here, and today we're going to discuss the first five problems of today's contest, education round 190. So, yeah. So, how are we going to discuss the problems? First, we are going to understand the problem as well as go deep into it using some examples, and then using those examples and understanding the problem, we will create some observations and intuitions. Then we are going to use those intuitions to create a final solution, and then we'll see how can we code it using the code I used to submit for this problem. So yeah, that's the framework that we are going to use. I did four questions for WA in question two. Question two was, I think I also did a WA here. Did I? Not actually. Okay, got it. Yeah, this was also a good problem. Beautiful problems today, actually. Nice problems. Didn't expect B to be DP. Oh, you used, okay. Yeah, we can say that that's a sort of a DP, but yeah, can solve it pretty easily using prefix suffix sums or some variation around it. So yeah, this could also be solved with logic, I would say. Yeah, we are going to discuss it in detail. So yeah, don't worry. B was just prefix suffix sum. Yeah, you can say that. I used a similar approach, or like, yeah, I used prefix suffix sum. So we are going to discuss in detail how to do it. So do ping out chat how many questions you all did, and then let's start with the very first problem. we we was just prefix suffix, but some people got hacked. Was able to do C, D got TLE in test case 15. I also use prefix suffix some. Not sure if mine is hacked, but yeah, not yet, but maybe was able to do till C, D got TLE in test case 15. Okay, D got TLE. Okay, B was just this. Okay, so let's start actually. Just give me 1 minute or like just few seconds. Yeah, back to it. Okay, my first contest on Codeforces solved two questions. Really great, dude. Really great. Third was easy actually. Like if you could solve first two, I think you can also solve the third one. We are going to discuss it anyway. So yeah, I did B with brute force. Okay, you're the same one who got a hacked, right? I'm not sure. One of my friend did as this is okay. Yeah, I did something similar, but I think the core idea remains the same, right? D was confused, very confusing case study. Yeah, let's go. Let's start actually. Let's start with the very first problem. By the way, like if you have already solved this problem, you can actually tell your approach, or if you find that you found something unusual or some better intuition or observation, you can always ping it out in the comment section. And even after the contest, like if you think something you want to share which is very valuable, you can ping out in the comments. And if you cannot get anything or like couldn't understand some part, you can also ping that out in the comment section. Let's start, chat. Let's start. Let's start with the very first question now. Yeah, optimal purchase. You have a group of N students who access an online course. Two types of access keys are available in the store. Okay, got it. Let's start with the very first problem. This problem A. So first thing we are given is that we have N students. Students. Okay, who needs an access to an online course, and there are two type of access keys available in the store. Individual key costs $8, gives access to one student, and the group key costs $B and gives access to a group of three students inclusive. A group key can be also used with fewer students, one or two. Its price does not change. The task is to find the minimum amount of money to provide access to online course for all N students. Okay, got it. Second part, we are given there are N students, right? And everyone needs a course. Everyone needs a course. Needs course, right? And there are some packages available for course, right? Each course has some access key here, and then we have to buy that access key. Each course has some access key. And access key are of two types. First is individual, or let's say single access key. You get a single access key, and the cost of it, The cost of it is $8, and you have a access key which is valid for three people, and the cost of it is B. Also, like less than three people can also use it, right? So this is the entire question that we have N students. Everyone needs a course, right? And to buy a course, we would need this access key. An access key we can buy, like we have two packages for buying access keys. First, we can buy a single access key, and second, we can buy a group of three, and here one. And we have to decide like what is the minimum cost. Third, minimum cost to buy access keys for everyone, access keys or like buy a course for all N students, all N students. This is what we need to find, right? Also, let's see the constraints. The constraints of the problem is all NAB, A is the cost and B is the cost. All are less than equal to 10 raised by 8. Let's see that. That this is a 4 point. All variables NAB are less than equal to 10 raised by 8. All also like greater than equal to 1. This is the entire question, right? We have N students, everyone needs a course, and we can buy access keys. Keys can be bought in bundles of one. If we buy one single access key, it will cost us one. If we buy three access keys, it will cost us three, right? And we have to find the minimum cost to buy access keys for N students. Got it? Let's see with an example and understand it more using some example. Let's see this 5, 10, and 25. So example, yeah, example, and A and B. And here is 5, this is 10, and this is 25. What does this mean? This means single access key cost us, single key cost us $10. What does this tell? This tells us three access keys. Three keys cost us $25. Right? But these three have to be used, right? This is sort of a shared access key that three or less people can use. Now we have five people, right? We have five people. Let's say there's 1, 2, 3, 4, and 5. These are the people. Now we have to buy as like we have to buy each of them access keys, and we want them to be as less as possible, right? So first we have to decide, right? There are like few conditions that you can see here. The first is what if this like we have these two bundles, right? There would be case where we would only buy this, and there would be case where we would only buy this, right? There could be three different cases. For example, let's say we have only three students. Let's say for this n equal to 3, what we would buy? If we buy only single keys, this would cost us 3 into 10, $30, right? But if we buy, let's say this package of three access keys, this would cost us 1 into 25, 25, right? That means this is best for this if we are buying three. But let's say we had four. Now for this one, this extra key, right? Either we could buy a single access key that would cost us 10, either we could buy a package that would cost us 30. Now here we would buy this because this is, sorry, not 30, it's 25, right? This is cheaper, right? That means we use both according to the utilization, right? So what we can do here is for every n, let's say for 5, now we have 5. This we know to take these three, best is to go with B, and that would cost us 25. Let's say now we have 2. Now again we can buy two access keys, two single keys that would cost us $20. Otherwise we could buy a single third key, that is B, 1 into B, or access key that goes with that can be shared with a group of 3, and that this would cost us $25. Which should we choose? This, right? So best answer would be here we choose the second package, here we choose the first package. So the answer is 25 plus 20, which is equal to 45. Let's see the answer. 45. Okay, great. So like what observations can we make? Observations is we have two choices. One we have choice for a single access key and one we have choice of packs of three. In packs of three, we could either cost us, it would cost us 3 into A, or it might cost us how much B, and we have to decide what to choose, right? And for single, again, we only have a single choice to buy it as A. Also, for single as well as double. For this two, we can buy a pack of three, right? What if like B is less than A? Then we can buy a pack of three. Similarly, for double two, we can either buy A or either buy B. Right. So let's see like what to choose and what not to. So the best possible way is, let's say we have n. First, let's say n is was 5, or let's say n was 8. So it would be 8 people. 1, 2, 3, 4, 5, 6, 7, and 8. First, we'll group it in groups of 3. Right. This is the remainder. And we'll find for these groups what is better, 3A or B. Let's say if B is better, for these groups we'll use B into number of groups. Or like mathematically, minimum of 3A comma B into number of groups. And what is this number of groups? Let's break it down more. This would be equal to 3A comma B. Number of groups is nothing but n divided by 3. We got this part. Okay, cool. What about remainder? How many groups will be left? This would be n percent 3. These are the number of people left. Okay, how to decide again? Either we could buy a B, a group of three. These n% 3 would always be less than 3. So we can always satisfy it using a package B or using an access key B. Okay, great. Otherwise, we have to spend 3%, n% 3 into A money. Again, we'll choose a minimum of it. That means a final answer would be minimum of B, that is cost us here. Otherwise, n% 3 star this whole bracket star A, right? So this tells us about the groups of three, and this tells us about the remainder. So this would be a final answer. I hope this is crystal clear. This is like typical question A of any div 2 or div 1 round, like not div 1, typical div 2. So yeah, it was pretty easy. Let's see my submission now. Here we go. Ignore the template, by the way, guys. It's just for like fast coding or like if templates are just for certain use cases, but yeah, just ignore it if you cannot understand it, or if you're a beginner, just focus on this part, right? Let's see it. Also ignore this line, debug this. This is just like some sort of function which helps me debug stuff. But yeah, let's keep our focus on this part. This is I'm taking an input here. This I'm just implementing the formula, right? I'm just doing it in parts. This three is basically number of groups, n divided by 3. Then our initial answer would be number of groups into multiplication of minimum of B, comma 3 star A. Now this is our remainder, and in our answer, I'm just adding remainder star A, right? Either using the package 1 or the access key 1 or access key 2, which is group of 3. And this just prints it. So yeah, this is our entire mathematical formula that we used. Did you guys get it? Oh, let's see. There are a lot of comments here. I didn't use, I didn't get the language of third question, mostly lead code earlier. Did lead not new on CF. Okay. Like I'm going to explain it. I'm going to break it down. If 3 star A is less than B, then just use A, else for this. If 3 star A is less than B, then use A else. Yeah. Else for multiple of 3, use B. If you have remainder left, take me. Yeah, exactly this. Exactly this. This is like exactly this. Yeah. I will absolve C. Yeah, sure. You can even go with D, like if you want. Let's go further. So this is a B question, digit string. So yeah, I saw many comments regarding DP and all, but yeah, you can easily solve it using simple code logic. Let's understand how. Digit string. So you are given a string S consisting of digits from 1 to 4. Got it? The B question, right? So given this first point, this string, okay, cool. Second point, and each digit will consist of 1 to 4, like each character, each character will be from 1 to 4. Cool. We have the string. Let's say that the string is beautiful if it's impossible to select some of its elements and write them out in the same order as they appear in string to form a number that is multiple of 4. Got it? For example, these strings. These are beautiful while these strings are not. Let's understand it. We are given the definition of term beautiful. And a string is beautiful if any subsequence is not divisible by 4. Is not divisible by 4. Right. In simple terms, it's saying that we have to, a string is beautiful if any of its subsequence is not divisible by 4. In very simple terms. For example, these strings. And the non-empty string is considered beautiful. Okay, cool. Your task is to create minimum possible number of elements in the string that need to be removed in order to make it beautiful. Okay. Third thing, which is what we need to find out, minimum characters to remove y to make s beautiful. Got it? Cools. And the third part, sorry, let's see the constraints. The length of string is 3 into 10 less 10 raised to the power 5, like typical standard constraints, nothing new. Here, the length is less than equal to 3 into 10 raised to the power 5. Right, so we have these 3 points that we have to consider, or like this is the entire question. We have a string where each character is ranges from 1 to 4, right? Then we have the definition of the term beautiful. Beautiful means any subsequence is not divisible by 4. And minimum characters to remove is will be a final answer that we have to find out. To why to make S beautiful. Let's see now. For each test case, print a single integer, minimum possible integer elements that we have to remove basically. Let's see some example. Let's take this. Sorry. Just 1 second. Okay, let's do it in this way. Who cares? We have this string. Cools. And now we have to find out, like we have to remove elements. So all numbers should like none of the subsequence. Subsequence means, let's say I took this 1 and 3. So this 1, 3 becomes 13. This should not be divisible by 4. This should divided by 4 should not be equal to 0. This is what we want. Here lies all subsequence. All subsequence. For all subsequence, this number divided by 4 should not be equal to 0. For some more example of subsequence, let's say I take this 2, then this 4, then some 2. But they should appear here in order. So 2, 4, and 2. I hope you guys are already aware of what subsequence means. But yeah, this is a definition. Subsequence means you can take some characters or like this is a string. So you can take some characters, otherwise you can take some elements in array or string, whatever. And you will use them in the same order as they appear in the string or the same order you are going to take, right? You have to take from left to right. So left 2, then 4, then 2. So here it is. And we have to ensure that all subsequence should not be divisible by 4, right? For this string, what numbers are divisible by 4? First comes the number 4 itself, right? Like if I take this, this is divisible by 4. This is like straight away menace, right? So we have to remove this. Similarly, this 4, we have to remove this. Now, what number? This 1, 2 is 12, right? 12 divided by 4 is equal to 0, 0. So we have to remove some character, right? Either 1 or either 2. Let's remove 1. What happens now? Now we have 3, 2, 2. 3, 2 is 32. Again, 32 is the alarming number. 32 divided by 4 is equal to 0. Again, we have to remove 32, 3 or 2. But notice something. We have 1, 3 and then 2 here. So if we have to remove these both, right? If we have to remove the 2. Let's remove this, right? So what we removed this, we removed this, we removed this, and we removed this. So we had removed 4 numbers. So the final string became 2, 2, 3. Let's check if 4 is the final answer. Yeah, this is the answer. Right, but yeah, it's like pretty confusing, right? What we will remove or not, right? Let's understand it more deeply. One thing you notice, right, from this example that 4 can never be here, right? Because I can just take this 4, a single element, for any string, like if I'm given 3, 4, I can just take this as subsequence. This would be 4, and this divided by 4 is equal to 0, right? So this is a menace, like we have to remove it, right? So yeah, this is our first observation. Always remove 4. Remove 4. Cools. Let's go step by step, right? Here we saw that 4 can never be here. We are pretty sure, right? 4 can never be. Okay. We did the first step that we remove 4. That means again, concluding from it. Now in our string S, we have 3 numbers, 1, 2, and 3. Right? Our string would have only 3 numbers because this 4, we have to remove it. Right, because any player or any like user can take this and this a subsequence which would consist of only a single element 4, and that would be divisible by 4. Thus, our string would not be beautiful. So we have to remove all these 4s. This is the first observation. Second, let's notice now we have 1, 2, and 3. Now we know that 4 is an even number. Right, that means any number, like if, for example, any number which ends with 3 or any subsequence which ends with 1. Right, this would never cause a problem. Only thing that would cause a problem with subsequence ending with 2. Right, there might be some numbers here, and ending with 2 will create a problem because these will end with 3 or 1, and both are odd, and this will never create a problem because this is an odd and 4 is even, right? It won't be divisible. But yeah, this might be divisible. Let's take the very smallest case of it. Let's say we had 2 at the ending and we have some number. This could be either 1, this could be either 2, so it would become 22, or this would be either 3, this would become 32. Is this divisible by 4? Yeah, this is divisible by 4. That means this is an alarming. We can never have this, right? I would say any subsequence you put, any subsequence, right? As it does not have 4, to be divisible by 4, it must be one of these variation, because we know the last element must be 2 because it's even. It's the only even element you have. It must be any of these. Is this divisible by 4? No. That means we are safe here. We can have as 22 or like any variation of it, because any variation 2, 2, 2, or like 2, 2, 2, none is divisible, right? So that means this is safe. Now we are like solving it for a smaller part. For this, like I'm just 1 second. Yeah, there are a lot of comments here. What about B then? Like 900 or like 1000? No, I think B was around 1000 to 1100. B was a good question actually. Anyways, yeah, let's solve it for subsequence. Either 12, we know the ending element would be 2. So it could be the first element could be 1, 2, or 3, right? So it could not be 2 because 2 is not divisible. 2 is safe. We can have this. And similarly for 3, this is also divisible, right? That means we have to take care of these conditions. What are the conditions? When 1 comes before 2 and when 3 comes before 2. Yeah, these are the two conditions we have to take care of now, right? Condition 1 and condition 2. This is our second observation. And using this observation, we can see that means both, can we combine those both statements and say 1 and 3 before 2 is a problem, is a problem, right? We can treat both numbers as equal now because we don't care about their value. We know that any of these numbers come before 2, it will create a problem, right? So what can we do to solve it now? Okay. So the statement here is 1, 3 before 2 is a problem. That means for any, like any array, let's say this is the array A4 and A5, any array, any array, if 1 or 3 comes before 2, this would create a problem, right? Sorry. Let's say we are at this index and we have to like, how can we use this to our solving? Like, how can we use this? This, like, doesn't this mean that, like, now we know one thing, all these digits will be 1, 2 and 3. Yeah, this is true, right? So what we can do is we can analyze this sentence and we can see that, for like, if we want this to be beautiful, beautiful, let's say we are standing here, we are standing at the second index and we want it beautiful, right? Either we can delete all the ones and three in its prefix, right? We can delete this, and we can also delete all the twos here. Let's actually go step by step. We want that this should not be before this. So there are few things we can do, and we know this will always be true. What? Remove all one, remove all two, remove all two, right? Because after that, the string will only consist of 1 and 3, right? And any its permutation wouldn't cause it. So yeah, it solves the problem. Similarly, the second thing we can do is remove all 1 and 3. They consider them as same, right? Because both serve the same purpose. Both should not be before 2. If we remove this, the only number remaining would be 2, and this would be only consist of 2, and this would not cause any problem because any of the subsequences not divisible by 4. So yeah, this is also true, right? That means we, if we remove all the 2, or if we remove all the 1 comma 3, this saves us, right? Notice one thing. We know that we have to remove, our final goal is 1 comma 3 shouldn't be before 2. So using this, what we can do is, for any array, for any array, to make this beautiful, either we can remove all this or either we can remove all two, right? And or either we can do both to some part, both. And okay, both. What if I applied this operation, removed all 2 to suffix and removed all 1 comma 3 to prefix? Doesn't it would solve our problem? Let's say this is the array A0, A1, A2 and A3 and A4. If I apply for this prefix, I apply to remove all ones and threes, that I will remove them. And similarly for this suffix, I'll remove all two, right? That means this suffix would only have 1 comma 3 and this prefix would only have 2, right? This means this array would look like this, and 1 comma sorry, yeah, 1 comma 3 will be after 2. Can I say this? If I apply this operation, that 1 comma 3, I will disappear all it from this prefix, and for I will disappear all 2 from this suffix. So our string would look like this. Here there will be some number of twos, and here there will be some permutation of 3 and 1. Right. So using this operation, I'll apply this operation for every index and check the minimum possible answer we could get. Are you getting it? This is the entire solution, by the way. Right? We know that we have to remove 1 comma 3 from the prefix, or like we have to ensure that it is not before 2. So if we remove this from a prefix, right, then we can remove all the twos from the suffix. So the suffix would have ones and threes. The prefix would have twos. So this could be our optimal match, right? So this was the entire answer basically. That for the prefix we can remove all the ones and threes, and the suffix we can all remove all the twos, right? And this would create a ordinal match. Got it? So for all prefix, for all indices, we check prefix ones and threes plus suffix twos, the count of it, right? And we add them and we check it for all indexes, and we basically do the minimum of all, minimum for all the indexes of it. I hope it's pretty clear. Travels back from 2 then into what if all twos is left? This is also a case. I think a lot of, let's actually see the code as well and then move forward, and then I'll see the comments. But basically this was the solution. The algorithm would look like something like this. Algo for all I, for I, for all I, we check prefix I plus suffix I plus 1 basically. Right, we are going to remove it. Although this suffix would calculate count of all twos in the suffix, and this will prefix will calculate count of all ones or threes in the prefix. And we have to finally, our answer would be minimum of the answer comma this entire value. This is what we need to return, and this we are going to print out. Just ensure that we also take the case where basically prefix ending and prefix n-1 and suffix 0. Basically the case where we took all the twos and all the ones and threes, suffix 0. We also take these cases, right? So this three, we are going to solve it pretty easily. Let's see the solution. It's like pretty straightforward, right? This is the part. This is how I was calculating. I was checking for all ones and twos. How? Anyways, this is the prefix array. This is the suffix array. Here I'm building the prefix array. Here I'm building the suffix array. Note that we have to remove all the fours. So number of fours will be removed. I will just keep it as an answer. And then here is what we are doing. Here, yeah, here is what we are doing. Our final answer. This dot is our answer. This is the prefix, and this is the suffix. Right, the same formula, and already I've like this we do from 0 to n, and then I have also added the constraints from n+1 to ensure that we also follow these two conditions, right? But the formula remains the same. You check both conditions, you check this, you ensure that all fours are already removed, and yeah, this is your answer. So basically we did two operations to solve it. Two operations were enough. Max two operations, we can also solve it with one, right? Also, like you can intuitively think, right? Let's say we had this, From somewhere we would have to remove all ones and threes, right? Or somewhere we would have to remove all twos. Because if we did not, like, if we remove it, all ones and threes, then it would not cause us problem, right? And similarly, we remove twos here, it would only consist of ones and threes and twos here, right? To get this array, we wanted this array as our final array, right? A final array would look like two, 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 and then some ones and threes, right? To make this, we noted that to make this kind of array, where we had this, we can take some like operation to remove all ones and threes from here, and some operations to remove all twos from here, right? This is a better intuition actually. Yeah. So this is was like what I thought. I created this array. This would be our final array. So how can we ensure that we read this final array, right? So let's move on and let's read some comments. Traverse from back if 2 then increment 2 count, if 4 then increment 1 and 3 increment 2. Increment overall count. I'm not sure what are you talking about, Aditya. Yeah, that's also a case if all twos are left. What I thought was delete all four. Find first I index from start, whether 1 or 3, and first index from add where 2. Then between this and start and end, this why is not this working? I can actually, you can ping it out in the comment section. I'll like reply your comments. That would be more beneficial. Keep track of ones and three together and two separately. Yeah, exactly. I thought either remove all one and three or all twos. Not actually, like it's more of a prefix suffix thing, right? We saw that the finally our array would look like this, or string would look like this, all twos initially and then ones and threes. So like let's remove this prefix, all ones and threes from prefix and twos from the suffix. I thought this not actually. These are also cases like yeah, you can solve it using it, but these are not optimal, right? We need minimum number of steps. I meant like start traversing from the back. If you found a 4, increment answer. Yeah, this part is clear. If you found a 2, then increment the count of 2 count. If you found a 1 or 3, decrement 2 count. Okay. Increment answer. It got accepted. Okay, got it. So you are doing something like, okay, if you found 2, you incremented. If you found 1 or 3, you decremented and increment the answer. Oh, you did like, oh, the like it's the same thing, I guess. I'll actually tell you in the comments actually. That's actually, we have to, we are behind the timeline. We have to understand the third question. But yeah, this is basically you are doing the same thing, like what I can think of. Let's actually move forward now. Yeah, no issues, dude, no issues. Let's actually understand it after the YouTube, like after the stream ends. I'll personally ping it out. Just ping out in the comment section after the stream. It's good to go. Okay, let's start with the third question, I guess. Arrange the numbers in the circle. You have cards with numbers, C1 cards with number 1, and C2 cards with number 2, and Cn cards with number n. Okay, you must take these three. Let's take this first. So, yeah, this is the third problem. First, we are given that we are given some array or something where we have this, and this tells us we have C1 cards of 1, C2 cards of 2, C3 cards of 3, and finally Cn cards of number n. Right? That means there is a card and there is some number in it. Right? For Cn, the number is n. We have n cards like this, Cn cards like this, right? In which the number n is written. And what we have to do, you must take at least 3 cards from the ones you have, arrange them in the circle so that the following condition holds. In every triple of consecutive cards, there are at least 2 equal cards. Okay. Second thing, these are the cards we have, what we have. Take more than 3 cards, more than 3 cards, more than or equal to. Right. This part, I read a comment where someone wrote, right, they couldn't understand the problem. You must take at least 3 cards from the ones you have. These are the cards we have, and we have to take at least 3 and then arrange them in a cycle so that the following condition hold. Right. So we take more than 3 cards or greater than equal to 3 cards. And then we have arranged them in cycle, arrange in cycle. Right. And after arranging in cycle, in every triple of consecutive cards, there are at least 2 equal cards. That means let's say we took 4 cards, A, B, C, and D. Right. These are in cycle. We have to ensure that for every 3 consecutive cards, let's say ABC is consecutive, 2 cards must be same. 2 cards must be same. Must be same. As you know, this cycle, if we flat the cycle, this would look like A, B, C, and D. As this is a cycle, we can also take this 3 consecutive cards, right? C, D, and A, because this is a cycle, right? C, D, A. We can take these 3 cards too, right? C, D, and A. And we have to ensure that 2 cards must be same here. So any 2 cards, either this, or this must be same. Okay, great. Formally, if numbers were chosen on the cards are these are the numbers on the card and they are arranged in a circle, the following must hold. For every I from 0 to k minus 1, there are at least 2 equal numbers among ai plus 1, ai plus 2 mod k. So this is actually the same thing. Or we can say formally, let's say these are our cards. These are the numbers which are on the cards, right? Then for every I, right, for ai plus 1 mod k, ai plus 2 mod k, these mod are done because this is a cycle. That means after ak, we will go from to a naught. That means this also tells us that these every 3 consecutive, 2 must be same. 2 must be same. Okay, got it. That means even ak minus 1, this, and this, 2 must be same, right? Because we have a cycle. Okay, what is maximum number of card you can arrange? Okay, this is what we need to find out. Max card you can arrange. Can arrange. Okay, sure. What are the constraints? The number of n is 10 raised to power 5, and for the number of cards that we have is around 10 raised to power 9 for every number, right? So again here, fifth point, I guess, this is fourth. N is less than equal to 2 into 10 raised to 5 or 10 raised to power 2 into 10 raised to power 5. So like basically typical constraints we have, and like for every I, Ci is 10 raised to power less than 10 raised to power 9, right? So this is the entire question. We basically have some cards here, right? We have C1 cards that have a number 1 on them and C2 cards that have number 2 on them, and similarly. Then we have to take more than 3 cards. This, what we have to take, we have to maximize actually. And like when we take it, we arrange them in a cycle and ensure that every 3 consecutive cards and the 2 cards must be same. 2 cards must be same, or the number on them must be same. The number of them on any 2 cards must be same. or like this is the formal definition of it. And we have to find the max cards we can arrange or we can take from the initial deck that we have. And these are the constraints. Let's understand it deeply with some example. So yeah, let's take this example. Let's take this example actually, 2, 3, and 4. So we have two cards, 3 and 4. What does this tells? That this tells that we have two cards with a number 1 on them. We have three cards which have number 2 on them, right? And we have four cards that have number 3 on them, right? And then we have to take cards to arrange them something like, let's say A, B, and A, right? Why? Because now every three consecutive, this is a consecutive and two cards are same. Like we have to arrange it like this. For example, let's try arranging it. Let's try one, then let's arrange two, and then one here. Why? Because we need two, or every three consecutive must be, any two must be same. Similarly, now what number can we put? We know that this consecutive has to be same. That means this number should either be equal to this or should either be equal to this, right? Whenever arranging A, B, and now we have to arrange or we have to put now any number now, we can either put B or either put A, right? Any of those, because we would require all the three cards to be consecutive. All the three consecutive cards, any two must be same. That's a constraint that we have to follow. That means I have to put either two here. Okay, great. Now again we have a value. Now I can put one or two, but one is consumed, right? We only have two cards of one. So I can put two here. Great. What can I put here now? Again, these two are already two, so I can put anything. Okay, this is also a new observation. Let's say we had AA, now I can put it here. I can put anything. Okay, great. So the number here could be, it could be three, right? We only had one number. We can also put two here. So we have two options, two or three, because these are the two cards that are remaining. Two types of cards that are remaining. Let's assume that we put two here. Now we again have a slot. We only have this number left. Again, these two are same, so three, 3, and 3. So yeah, this is our final answer. But are you sure? Are we sure this is the final answer? Why? Because this is cyclic. That means this 3, 3, and 1. This also should also have same number of cards. But yeah, this is 3, and this is 1. 3, 3, 1. Last second, this is, let's say we have n card, this is n minus 1, and the first index. Yes. Oh yeah, first. Yeah, this is also true. But what after we take n, nth element, first element, and the second element? This creates a problem, right? This breaks it. This breaks it. We have to take care of circle now, because this, you can see clearly it breaks it completely. So what we can do, right? One thing you can notice is, you can, instead of this two, if we had one, this would have helped, right? What if we had this one here? Then these two, like we replaced, then we would have two, and then we would have three. Is this a valid number? Yeah. You can see, you can actually calculate every three consecutive numbers, two will be same, right? So like, this tells you something like, can we put numbers as the way they are? By the way, this is valid. That means we used all cards. That means eight. Eight is the maximum answer we could get. Let's check first. So we did for test case number two. So test case number two. So actually, sorry, my bad. There are total nine cards, and yeah, nine is our final answer, not eight. Okay, cool. Cool. So how, like, what can we do now? We got something right that here we failed due to the last and the first elements were not equal, right? We have to all like ensure that this does not happen again. Also, we notice something that if we arrange them according to their numbers, this pretty much works, right? But also, like, there is one more thing that we have to notice. What if we have only a single number here? Let's say, let's take one more example, which is 1, 2, and 4. Now we have 1 here, only one occurrences of 1, two occurrences of 2, and four occurrences of 3. Now, let's say we want again post it like how we had it, 2, 3, and 4. Now this creates a problem. Why? Because if we take this element and then this creates a problem because this only has one frequency. Its frequency is only one, right? That means this can never be equal like in any consecutive trio. We want some number to be equal to or two elements to be equal, right? But this cannot never be it because it only has single element. Okay, so this is observation two, right? That single frequency creates a problem. Otherwise, we can just arrange them like it, right? Because every like three consecutive elements, this or this, if we took go outside it, it would take two elements from it, right? Let's prove this first. Let's say we had some numbers A, then some B's, and then some C's. If we arrange them in the line, right? If we arrange them in the line, dot 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 some B's and then some C's. Initially we had A's. We know that we check for every three consecutive numbers, right? For every number we check inside it, this would always be true because this entire array consists of only A. So any subarray would always be A if we check inside it. Otherwise, the only problem it will take on the boundaries. On the boundaries, if I take two elements of it and one element of it, right? Either the boundary would be we take two elements from it and one from here. Either we take one from here and two from here. There are only these cases, right? So if we take two here and one here, it's also solved because we take two A's here and these both are equal. So yeah, this is fine. And again, if we take one element here and two here, this is also cool. Why? Because this, now we are utilizing this as power, right? So this tells us that arranging them together is fine. Together is cool. Right, this takes care of everything. Also, it takes care of the ending. Why? Because again, inside any subarray, this would always be true. And in the ending, either we will take one element, either we will take two element. If we take two element of the ending, like ending array, this is cool because it will take two elements of CC or two elements of ending element, whatever we have. And if you take one element, it will take two elements here. And this is also cool, right? That means arranging them together is cool. But when the problem arises when any element has frequency 1. Why? Because let's say we have again elements A dot 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 A, all A's here, then all B's here, then a single C here, then all D's here. We just saw that when we arrange them, all the internal subarrays, all the internal three consecutive elements will always have two elements that are equal to two, or equal, right? So it would always satisfy. And from the ends, we can take one element here and two here, right? Either we can take two here and one here, all will satisfy. But this case specifically, when we take one element from it and two from others, we cannot apply here, right, in this junction. In this junction, if we take one element here, this would be B, and two elements, this would be C and then D, because C does not have two elements, right? So we came to know this was our first intuition that came to our mind that we can just arrange them accordingly. But when can it cause the problem? This is our second intuition or second observation. It causes problem when the frequency is 1, because this case where like we take one element from this series and then two elements from the another series, as we don't have two elements here, this would cause a problem. Okay, great. What does this tells? This tells us that, okay, ignore the ones, ignore frequency equal to ones. We can do this, right? But the case is we want maximum cards, maximum cards here, maximum cards, and like we have to select maximum cards in our arrangement. We want maximum cards in our arrangement. This is what we want. What can we do? Like, how can we solve this? Like, if you analyze the state problem examples, like enough, like examples were pretty enough. All the variations were already included in the examples itself. And let's actually understand now back to where we were. We need maximum cards in our arrangement. So what we can do is, what if we did something like this? A, then we know that all the A's we have, and here was C, and this creates us a problem. What if we push this A here? Then this would become A, C, then again A. Now, if we take one element from here and two from here, this would give us ACA, right? But this is true. This is observation number 3, that this works, by the way. But this only fails when we have element after it or series after it. Let's call each consecutive number of cards that we have a series like. So this, let's say we had a series of D here, but this would create a problem here now, right? Because if we take one element for this series, we take one here and two here, this would create us a problem. So let's, instead of one, let's put two elements here, A and A. So this would become like series A, it ends here, then single element, then A, and then series T. Oh, cool. This saves it. This saves it, right? Because now we can take this permutation, one here and two here. This saves us. Again, if we take one from this series and two from here, this also saves us, right? Okay, yeah. Where were we actually? We want maximum cards in arrangement. That means we want max cards with frequency 1, frequency equal to 1 in our arrangement, right? So this is like how we are dealing with, like how can we include in our arrangement. So this is first thing that we can do. And I think we can extend it further. Like for A, we can make C here. Then again, we could take two A's here or some series again. And then we could even have, let's say, E, then again two A's, and then a series of T. This would also take, this is also fine, right? Until unless we have more than greater than equal to two A's here, this is fine, right? That means for any series A, to how many max frequency equal to 1 it can handle. Our condition is initially we should have two A's, the minimum number of A's, then some number with a frequency, then again two A's to complete it, right? Then again some number, then again two A's, then again some number, then again two A's. Right, this could work fine, right? This is how like we can take the maximum number of A's. Let me also open the question side by side. By the way, folks, if you have any doubts, you can always ping it out on the comment section. Now, moving forward, just 1 second. Let's go side by side. I'll tell you the code. Yeah, this is like the maximum number of, what is the maximum number of like frequency one we can handle for any range. We can handle at max. Uh, let's say its frequency is f dash. So f dash minus 2, because we need these two as our initial elements, divided by 2, the number of pairs we can make, right? We can handle these many elements for each range. Similarly, for B2, we can handle these many, like for, let's say its frequency f double dash, this would be equal to f double dash minus 2 divided by 2. Yeah, this is what we have. This is a formula what we have, right? It's different from code because like in code I'd use a separate approach, but yeah, this works. For every range, right, we can take these many number of frequency ones with us. Similarly for this, so these many number of frequency ones, right? Just one edge case that we noticed here. Here we notice that if we keep it ACA, this test case, for ACA, right, what we are doing, we have a frequency 2 here, and we are using it to keep a frequency 1, because now you can see this is also valid, right? But if you use it, like what's its frequency? The frequency of A is 2. So 2 minus 2 divided by 2 is equal to 0. That means you can take 0 number of A's. Why is this valid? This is a special case. But when this case occurs, when only one element or one card has frequency greater than equal to 2. Why? If it has frequency greater than equal to 2, then this it would look like this, and we can only keep we can sure that instead of putting two elements on the right side, we can take only one element here. We can put C here. Why? Because initially it's also A. On other cases, what occurred was if we took A here, we could say C here, and then we take two elements of A. We also used to take two elements of A because we know that some D exists with its numbers, right? After A, some D exists, but we know that for this, like when no D exists, we can only keep one element and ensure that a cycle exists. We have already seen it somewhere, right? Here initially there were only one, like we are there was this array initially, and we only took one A here and put like this, arrange it arrange it at the last. But when D or like the any element or any card whose frequency is greater than 2 occurred, it creates a problem. Why? Because when series of A ends, series of D starts, and when series of D starts, we have to ensure that the endpoints are safe. Endpoints will be safe when we take one element of D here and two elements previously, and there's these two elements must be equal now because we took one element from some other series. Right. So this is an edge case. When only one card with frequency greater than 2 exists, then we can take one element, we can paste it here, and this will help us to basically take one more card with frequency equal to 1. Right. So we have a this special case, as well as for every series, we can calculate how many extra cards we can pick. Right. Using these two intuitions, we can easily keep or easily maximize our count, right? So our answer would be first we will check the special case, right? And second, what we would do is for all series, right, we would use this formula f minus 2 divided by 2, and we will add it to some, let's say, extras we can keep, right? And then we will just increment our answer. This answer tells us how many cards used, and while using these series, we'll also increment our answer by f, because we are going to use all cards of it, because this f is greater than equal to 2, right? But if this f is equal to 1, right? What, let's say we have d cards where frequency is equal to 1, right? So our final answer would be the extras we can keep, minimum of extras we can keep, comma, this d, the number of cards of frequency equal to 1, right? So this would be our final answer. Let's show the code. Before showing, let's actually see the code. This is our vector. I sorted it in decreasing order, so I get the number with highest frequency, like first. Here is the condition. This condition is special case condition. When the number of elements are greater than 2, the first element or the index 1, the element at index 1 or the second element, it's equal to 1. When it's equal to 1, that means we only have single element which is greater than equal to 2. Here we are checking if the first element is greater than equal to 2 and the single element after sorting it in decreasing order, right? This is equal to 1. Then we keep this variable exx equal to true. And this exx basically does the same work as our like this extra variable did, right? So here I'm just iterating the entire array. If this is equal to, if this is greater than 2, this extra is being calculated here. If you break this down, this formula, this would result in same as what we calculated, this f minus 2 divided by 2, right? These both are same, right? I use 1 plus I minus 4 divided by 2 here. What I used, what I used, 1 plus I minus 4 divided by 2. If we open it, this would be 2 plus I minus 4 divided by 2. So this I is actually the frequency. Let's name it frequency. This would again f minus 2 divided by 2. Why this formula I chose? This one tells us what I did was, let's say I had some number of A's and then this C, which is again, so first I will, for the first, to keep the first card with frequency 1, we have to use 4 different cards, right? And subsequently after it, we would only require 2. I used this strategy, but yeah, it's basically the same thing, right? This formula works. Yeah. So this for all the numbers, this extra I'm calculating. So if I equal to 1, if extra is greater than 0, then we will use this extra element and increment our answer. Otherwise, if exs, if the special case arises, right? If exs, we will use this exx and this would become false and answer would be equal to, will increment our answer. Also, obviously, like instead of this, we could just increment this ex or the extra variable, right? We could just increment the extra variable here and this would work fine. Again, we have to take more than 3 elements. That's why if answer is less than 3, that means we have chosen less than 3 elements. So answer would be equal to 0. And finally, we are printing the answer. D1, yeah, now we are going to discuss the D problem. So yeah, cool stuff. Also, what was approximate rating of D according to you? Let's see actually. We are going to discuss the D problem as well. I hope this is super crystal clear. If you have any doubts, you can always ping it out in the comment section. D was around, I would say, 1600 or 1700. I'm not sure, like around from 1500 to 1700 if I have to give a range. Yeah, now let's discuss D now. Yeah, let's discuss D. So Alice and Bob, yeah, Alice and Bob decided to watch a TV series consist of n episodes, numbered from 1 to n. The series will shown on television over the next n days. Got it? Let's put it. This is the problem number D. Got it. So we have n episodes. Unfortunately, they live in different cities. The episode schedules may differ. On the I-th day, the A-ith episode will be shown in Alice's city, and the B-ith episode will be shown in Bob's city. Okay, got it. So we have two people, two persons here, Alice and Bob. On the I-th day, A-ith episode will be shown here. Episode. And similarly here on the I-th day, B-ith episode will be shown. Right. So basically we have some series and the episodes are randomly arranged here. Right. For Alice and Bob both. They plan to select a segment LR to watch a series. Initially, neither of them has seen any episodes. Each day I this segment follow this segment the following happens. If Alice has already watched this episodes 1 to A minus 1 but not AI, then she watches AI on the day I. Otherwise, she watches nothing on this day. If Bob has watched all the episodes 1 to BI minus 1 but not BI, then she watches BI on the day I. Otherwise, he watches nothing on this day. To avoid spoilers in their conversation, Alice Bob want to choose some segment LR such that every day in this segment, one of the following thing happens. Either they watch the same episode, either neither of them watches anything on that day. Help calculate Bob suitable Elena. This part is like I will explain it actually. Let's go. So you know that Alice will see some AIth episode on the ith day, and Bob will see BIth episode on the ith day, right? So for Alice, there would be some array A naught like A1, A2, A3, right? And some Bob, there would be some array B naught, B1, B2, and B3, right? And let's say what condition we have here is for any day, let's say we are here, right? If we have watched all the episodes from zero for Alice, for example, we have watched all episodes from 0 to A2 minus 1, right? We have watched all these episodes, then we are going to watch it. Similarly, that goes for Bob too. If we have watched from all the episodes from like 0 to B2 minus 1, whatever at this element could be randomly by the way, B2 minus 1, we are going to watch this episode, right? And what we want is some segment LNR, right? That we start from Lth day, both start from Lth day, right? And both watches same episode on each day. On each day, this happens. Either they both watches same episode, or neither watches anything. Neither watch anything, right? Either they both watch the same episode, or neither of them watches anything, right? This is what the segment that we need to find. Let's explain this part even better. Let's say we are at here. This is Alice's array 0, 1, and then actually 1, 2, 1, and 3. And this is 3, 2, 1, and 2. As you can see that here is also 2, by the way. Yeah, yeah. Let's say we have this. This is for Alice and this is Bob. On the first day, first episode number 1 is shown to Alice and episode number 3 is shown to Alice. And on the second day, episode number 2 is shown to Alice and episode number 2 is shown to Bob. Right? We are just like understanding the question in depth. So I believe if you like understand the entire question in depth, this like really helps you to solve the problem. This is the very first step towards solving any problem. Yeah. Continuing it, this is what the problem says that at the second day, the second episode is shown to Alice. Also, the second episode is shown to Bob. On the first day, the first episode is shown to Alice, and the third episode is shown to Bob. Now we want some LNR or some range of days, right? Let's say like this days, so that both conditions occur that both of them watches the same episode or either neither watches. For this, what would be that LNR? It could be this. Why? Because neither to watch an episode, to watch this, it must have covered all the elements starting from 1 to AI minus 1. That is, it has to watch 1. When we start from here, we would initially we cannot watch, like we haven't watched any episode. That means we will not watch this. Similarly for Bob 2, we will not watch this. So yeah, we can say that one LNR could be 2 comma 2. We are taking one base indexing, by the way, right? Another LNR could be what? Let's again type it here. 1 2 1 2, and this is 3 2 1 2. You can also take this. Why? Because this is the first day. Alice will watch and Bob will also watch on the second day. This is 2. And we have already covered all the elements from 1 to 2 minus 1, which is only 1. Have you watched the first episode? Yeah. It's just like simple maths. Like if we have watched all the episodes before the episode number 2, then we are going to watch it. So yeah, we are going to watch it. We will watch it this. Yeah, we are going to watch it. So yeah, we can take this as LNR2. So this would be equal to 3 comma 4. So this is also a valid. And what we need to find out? We need to find out, calculate the number of suitable segments of LNR. That means we have to find out all suitable LNR, right? Total number of LNR. Find total segments, total valid L comma R segments. This is what we need to find out, right? And like what we can do to find it out, we'll see it, right? But this is basic the idea that entire segment we have to watch both elements. Can I take this as LNR? Now this creates a problem. Why? Because Alice will watch the episode and this Bob will not watch the episode, right? And we cannot do this, right? We would always want the Alice to watch. If Alice is watching, Bob should watch the same episode, right? So both must watch, right? This means both must watch. Both must watch or don't watch. Don't watch, right? Let's study it step by step. Let's study when will we don't watch anything. Like what segments will we when we don't watch anything at all. Let's take here some example. By the way, constraints of array are also like standard constraints that we then is less than equal to 5 into 10 raised to power 5. And all the elements or the number of episodes would be, it would range from 1 to n. Any like the ith episode would range from 1 to n. So yeah, the standard constraints basically. You have to solve it from big O of n to n log n or something like on those lines, right? Yeah, back to question. So let's say we have this array. So first we see that we need all the valid LNRs, right? Where we don't watch the show. Sorry, where we where we both either watch the same episode or either we don't watch any episode. First we take all LNR where we don't watch any show. Where we don't watch any show. And when will both will not watch any show? When one doesn't appear. Doesn't appear. Right. The person, let's say we had this range. You know that neither Alice would be able to watch the show, neither Bob, because we have not watched the prerequisite shows. Right. And the number one prerequisite is the number one, the first show or the first episode, basically. We haven't watched the previous episodes, and the number one requisite to watch is the episode number one. If we haven't watched this, we can't watch any episodes. Can't watch. If we can't watch, that means both can't watch, right? Both can't watch. That means it's a valid. because in an entire array both will not watch. And yeah, our condition is either they both watch just at the same day, either they don't watch. Again, yeah, it also matters that we watch the same episode, but if we watch the same day, right, if we watch the same day, it wouldn't matter, we will watch the same episode. Let's take this example. First we both will watch episode number 1, then 2, and then 3, right? If we watch, we will watch the same day. And let's say we have 4 and 5, we will skip it. We will both don't watch and then again watch. So yeah, this comes us the first observation, which is all the subarrays that doesn't have one, well, definitely will are valid LNR, will give us valid LNR, right? Why? Because if it does not have one, both Alice and Bob will not watch any shows in the entire time, right? So either we could make them watch the same day, either we would not rather not watch the same day, both will not watch. So yeah, this is the first test case that we are. How can we find this? Like basically we can find all subarrays that doesn't have one in both array A and array B. Let's say this array that keeps us all the tracks of LS is A and this array is B, right? Then we would require to find all the subarrays in it. For example, let's say 3, 4, 5, 6, 7, 8, and then we have 1, 1, 1, 1, 1, 1, and 1, 1. Now we are like this is the subarray. This subarray does not have anyone. Does not have one. We could find all the longest subarrays that does not have any one, or for every index we would find the last index where we had one, right? And we will make all possible cases, this and this. So we have two cases here, right? This is the approach I used. For every index I chose, I looked where the last, this could be 4 2. We need one on either side, because if either side had one, this makes this watch the show, right? And we want the first, we will conclude all cases where both LS watch didn't watch any show. We used this technique. We saw the last one we had at index number 2. So from index number 3 to 4, we will make all the possible subarrays that ended at this index I, right? So this is the algorithm we use. Algorithm: for every index I, for every I, find number of L comma I, and this number of L comma I would be equal to I minus previous one's location. You can easily calculate previous one's location using some vector or some even variable, right? So yeah, this is the first part of the problem, where we just took all the subarrays where neither Alice and neither Bob watched anything, right? Now, second part, they watched one greater than equal to one episodes. Just notice something. They will watch an episode when both X and X appears here, right? Then that means both numbers are same. If they watch, there must be 1 comma 1 in their subarray somewhere, right? And there may be some elements on the left and some elements on the right, right? This was my first intuition that came to my mind. The first was, let's say if they didn't watch episodes, then I can easily calculate it, find the subarrays where there is no one, and then easily calculate either in the subarrays, either I can see for every index the number of L comma I where this ends at I, right? So this uh, this would be equal to I minus P, which is the previous location of the last one we basically had, right? So I can create all the this array and then this array, right? This part I hope is crystal clear, right? This was something like this: 3, 5, 1, 1, and 7 and 2, and then 3 and 4. Let's say we are at this, right? We need the number of arrays where we could do 1 comma L comma I. I is here, If we are taking one base indexing, this is 1, 2, 3, and 4. So I is here 4, 4 comma L. So what else we have? We can either do this 4 comma 4, either we can do 3 comma 4, either we can do 2 comma 4, either we can do 1 comma 4. But we cannot do 1 comma 4 because it has 1 in it. So we will take the previous location, previous 1, I minus previous one's location will give us. Why? Because this is I and this minus this. 4 minus 1 is equal to 3, and we will have 3 subarrays. Basically, we start from here. This is 1, this is 2, and this is 3. This part, this number of elements here, we are calculating this using this formula. This P, we can either take some. I took an array because we are going to use this value again later on. Right? I initially used a variable, but yeah, use an array, we are going to use it. I'll tell how. This is when we watch 0 episodes. Now we watch greater than 1. So it would look like this. We will have 1 comma 1 and then some episodes on the right. Now we would want that, let's say on the left, there could be any number of elements, but there could not be one. No ones, right? Because if any one occur here, right, the person Alice or Alice would, let's say here is 1 and here is 3. Alice would watch this episode and we want both of them to watch on the same day. So this would not, this would defy our defy our valid segment. So what we can do, we want that initially this should have no ones, no ones, no ones, right? And on the prefix, on and the suffix, what we have to care now. Now we have to take care of 2. If 2 comma x does not exist, because if 2 comma x exists before the 2 comma 2 occurs, if 2 comma 2 occurs, again we will watch the episode. But if 2 comma x exists, then here's a problem. Why? Because the Alice will watch. Alice watches, right, which creates a problem. So 2 comma x shouldn't exist. Okay, got it. To calculate the prefix, it's super easy. We can use this this priv index, where priv I tells us location of previous one or one before it, one before it in both A comma B, right? We can use this prefix pref array to calculate the number of elements here. Why would want number of elements here? Let's say for any valid element that or any valid segment that we are watching, we know 1 comma 1 must be there because we are watching greater than equal to 1 episode. That means 1 comma 1 will always be there. And prefix, there must not be like element, and that, let's say this entire segment is valid, right? That means all subarrays will be valid. Subarrays will be valid. Will be valid, right? And we want all subarrays that include 1 comma 1 because we have already calculated all subarrays where we don't watch any episodes, right? So for this, how many subarrays will be there? All subarrays arrays with 1 comma 1 will be valid. Will be valid, right? If this entire array is valid, all subarrays, this part would also be valid, this part would also be valid, this part would also be valid. Similarly, this part would also be valid, but we must include this. So let's say if this total number of elements on prefix, including this, is x, and total number of elements on the suffix, including this, is y. The total elements that will be valid, that would include 1 comma, but would be x into y, right? That means if we calculate this from here, and then we calculate this from here, we will get our answer. This is the total length which would be valid. It would have 2 comma 2 and some 3 comma 3 and any number of elements, but it would start from 1. Also, like, it should not have any 1 before, because if it had 1, Even 1 comma 1 it had, we would calculate for all individual 1 comma 1s, right? This might even have this 1 comma 1 here, but it doesn't matter because in the prefix we take as much elements we can take, but any one should not be here, right? Because we want this element to be the starting element, starting, right? If we take this as a starting element and then calculate it, then we can find some number of subarrays that would be equal to x, number of elements in prefix, and y, this x into y number of subarrays, and we'll add it to our answer. These rating is around like I think 1500 to 1700, like this range. So yeah, anyways, this is like how we calculated this part way we will calculate. We already calculated how we are going to find the number of elements in the prefix that must be valid, right? But we haven't find how can we find in suffix if what range would be valid. To calculate the suffix, we will see it, right? This part is remaining, right? So to calculate the suffix, let's say we start from 1 comma 1. How we will check what suffix is valid? Because after 1 comma 1, we would not want any two to be alone in Alice's or Bob's, right? Because if this occurs, that means Alice has watched and Bob has not, right? This is a problem because we want both of them to watch together. So we would want, instead of this, something like this would happen. After some elements, let's say 3, 4, 2, and 2, they occur both together, right? And similarly, let's say 3 and 3 then occurs together. And if let's say 4 occurs here and 5, this is a no-go, right? Because here Alice would bob first. So we will take this arrangement, this array, and we'll take this is a valid one. This is valid. And then using it, we will tell that all subarrays will be valid. Subarrays with 1 comma 1 will be valid. Will be valid. And how many subarrays we have with 1 comma 1? Let's say this, its prefix as 5 comma 5. I told you this is equal to a comma b. A is the previous elements, the previous number of elements that does not have any 1, right? So this would be here is equal to 2, including this element itself, right? And similarly in the suffix we have 1, 2, 3, 4, 4 elements. So it's 2 into 4, which is equal to 8. Yeah, it's working. So yeah, this would give us 8. So 8 subarrays would be there. We can even break it, right? So this would be equal to 1 comma 1, and then 3, 4, 2, 2, 3, 3, right? And then we had 4 and some, let's say 5 here. So this is a no-go. And here we had, let's say 5 comma 5. So we can take this segment, then this segment, then this segment, and then this segment. Similarly, we can take this segment, then again this segment, and this segment. That's why we take A into B, because we might choose some length here, and then we might choose some length here. That's why we came to the conclusion of A into B. The problem is how are we going to decide the suffix? Let's see. What I did for suffix is we know that, right? We know that 3 comma 3. We know that after 1, we would like we would like the location of the next 2, right? And we would like to know would where this 2 ends. For example, let's say we had this 1 comma 1, and then we had 3 comma 4, 5, and then we had 2 comma 2, and then we had 7 comma 6, and then we had 3 comma 3, right? This is like the best array. We start from here. We want to find what elements are valid here, till where we could find valid. We would want to know where the next 2 comma 2 uh, is there, right? And we would go here, and we have to ensure that in between no 2 occurs. No 2 occurs, right? After this 2 comma 2, we would have to go to 3 comma 3. and then similarly we would go on. So you can see that. And here, what would happen here? Uh, Here again we are at 1 comma 1, and the next two arrives here, which is 2 comma 3. So we will stop here. Similarly, like after 3 comma 3, we'll go 4 comma 5 and we'll stop here. Whenever we reaches some element which is not like equal on both sides, we'll stop. That means this is the final array, right? And this is like how we are going to approach it, right? We'll keep going and then see. But this might result in TLE, right? Because going each time. Using n square, we can easily calculate it. We would go start from here and then keep on going again and again and check if like it breaks or not. We can easily calculate it, but we have to solve it in n. So what we can do here? So we know that that after 2, we have to check the suffix where or the subarray starting from 2, right? The longest subarray starting from 2 such that this is valid. Now you can see the question shifts to the number 2, right? And similarly, the question shifts after it to the number 3. Now we want the longest array that starts from 3 comma 3 and goes as large as it can, right? So to calculate this, used a map here. And what I did was I calculated all chains in suffix, right? What does this mean? For example, let's take this array again. 1 comma 1, 3 comma 5, 2 comma 2, 7 comma 6, 3 comma 3, and 4 comma 5. After this 1 comma 1, how would like I would like to know, you know, each like let's say if I start from 2 comma 2, let's say we both have watched 2 episodes. What if I have some DP, right? Here DP, which stores the length or the suffix which is valid for this, right? Which is valid for this. Let's say DPI stores length till there it's valid. Till there it's valid, right? I basically calculate this DPI by iterating from last to first. So this DP1 comma 1 just checks this DPI, right? The DP2 tells us again, what if I keep this map that I'm telling, its name is, let's say it's a DPI, and DPI tells us if we start from if we have done I comma ith episode, what's the index till where we will go, till where the array would be valid, array will be valid, right? So DP1 gives us answer. DP1 gives us the index, this index, right? Till there it was till there the subarray would be valid. If I started from 1 comma 1 here, what would be the index that here it would be valid? So DP1 would be equal to nothing but DP2, right? If DP2 exists, if DP2 exists, or this would be equal to n, because this not only for 1 comma 1, if this I occurs either in Alice or Bob, because if it occurs on Alice, that means we have watched the episode here and we will break it, right? For example, for this 1 comma 1, this DPI would be equal to DP2, right? If DP2 exists, right? If DP2 exists, because this will be equal to the maximum chain it could have on the right side, right? The maximum element till there, this if we start from this here, if we have watched the second episode, what's the maximum number we could get on the right side? Otherwise, if it's DP, if 2 is not there, this would be equal to n. the last element, because no 2 would exist in the suffix. I hope you got it. This DPI, if ith episode is watched, what index, watched till what index will it be valid? Will array is valid. For example, if we are at 1 comma 1, 2 comma 2, and 3 comma 3, and 4 comma 4, let's say we started from the ending. This dp4 should be equal to the number 4. If we are taking one base indexing, by the way, indexes here are 1, 2, 3, and 4, right? Because if we start at the fourth, if we watch just the fourth episode, we should end here. What this dp3 should be equal to? This dp3 should be equal to dp4. Why? Because we are going to watch it, right? This would be equal to 4, and this is our answer, right? This is the index where we will end it, right? If we watch the third episode here, we will end the fourth here. Similarly, dp2 would be equal to dp3. This would again be equal to 4. That means if we start watch the second episode here, we'll go till the end, till the index 4. And similarly, this dp1 would be equal to dp2, the next chain basically, or the next occurrence that we want to find. And this was also equal to 4. That means if we started, we watch the first episode here, we'll go till the end, till the very end. What if some like culprits exist? What if this exists? This is 1 comma 1, and this is 2 comma 3. Now, what would be for this? Now we have to note that it has both 2 and 3. So we will do dp2 equal to I. That means if we watch the second episode here, we will end here. Like if we take this, we will end here. Why? Because dp1 would be equal to, sorry, so this has to tell the index that we will include, right? So yeah, this has to go, this 4 instead of 4, this will tell us 5. The number till where we could go, and we will not conclude the last part. Otherwise, what we have to do is we have to subtract it, because if we start the watch the second episode here, we cannot watch the second episode here, right? So we will do I minus 1 here, because we can't, like what this TPI tells us, if we watch the ith episode, till where we can go such that the array is valid. If we watch the second episode here, we cannot watch the second episode here, right? That means we will go till I minus 1. So an index minus 1 here. Okay, great. So dp1 would be equal to dp2. This is equal to I minus 1. This is again equal to, this I was 2. This was 1 here. 1. That means if we start from here, we'll go till here. Super cool. Right. So this is what the DP tells us. We will start from the ending to the beginning. Right. DPI. If both the elements are I comma I, that means we will go further in the chain. That means we can go further. This is valid. So this would be equal to DPI plus 1. What if no elements exist? For example, 1 comma V, 3, 3, 4, and 7. And let's say this is also 3. Again, we will start from the suffix. dp3 would be equal to 2. Again, dp7 would also, let's say we have watched the 7 episode here. This would again be equal to 2, because we cannot watch it here, right? Let's say we watch 3 here. Again, we cannot watch it. So this would be equal to, or also dp3 would be equal to 1, and dp4 equal to 1. I minus 1 basically is equal to I minus 1. Because when we watch 3 here, this would actually invalid array. So we go I minus 1 here. Now for 1, right? This is 1 comma I, right? Both elements, sorry, both elements are same. This is x comma x. Both are same. Now what to do? This would be equal to dp2, but 2 does not exist. That means in the suffix, no 2 exists. No 2 exists. Doesn't that mean that we can go till dp and which sorry, we can go to nth element. We can go till the ending, right? This is our final array because every suffix or sorry, every prefix would be true, right? Because when we start from here, if we have no 2 in our suffix, that means after it, no shows are watched. No shows are watched. That means all are valid. All are valid, right? So this is basically what we need to do to calculate the chain, right? Start from the ending till the beginning. Let's take some example, I guess. Let's 3, 2, 1, comma 1 and 4, 5, comma 4. Yeah, 1, comma 1, 3, comma 4, 2, comma 2, again 1, comma 1, 3, comma 4, 2, comma 1. Now, let's start from the ending. dp1 would be equal to this minus 1. By the way, indexes are 1 base. So this is 1, 2, 3, 4, 5, and 6. So this would become 5. And dp2 would become 5 or 2 because we cannot start it. Again, here, same thing would happen. dp3 would become 4 and dp4 would become dp4 would become 4 again. Now here, both are true. So this dp1 would be equal to dp2. This dp2 is equal to 5. So till 5, starting from 4 to 5, till here, this is the max element. This is a subarray. We got the subarray. We got the right side, right? If this right side was B, right? What we wanted to find out? We wanted to find out the total LR when we watch at least one episode, right? So we had one here. So for this one, what I would do is I'll store this value for every element using this the DP we had, the dynamic programming vector we had, or the this would be map probably, or the vector would also be fine. I used a map. Again, 1 comma 1, I would know the length at max it would go, right? This length we would know. This is B, and this we already know from the priv vector. This is A. Finally, we will do A into B, and this would be increment this into our answer, right? Let's summarize this. Summarizing. First, we calculated all where we watch no shows. All LR where no shows were watched. No shows. And then we calculated all LR where at least one show. At least one show was watched. To calculate this, we calculated ranges where no one were there. No ones. Because one was the first episode that we, no shows or actually episodes. Shows is a wrong word actually. No episode. Because this one was the first episode that we anyone needs to watch, and if there is no one, that means both Alice and Bob did watch any episodes. So we calculated this, and then at least one episode. We calculated this. We took for all ones. Let's say this is the starting. We will take the prefix where we will find the number of elements where no ones exist, no ones, and the suffix where this chain is valid. Right. That means every array or like every subarray that has this would be valid. So let's say there are A elements here and then B elements here, including this would become A into B. For all starting points, so for all 1 comma 1, I'm going to add this. And then we are going to add this answer plus equal to frequency, whatever we got here. And this would be a final answer. Let's see the code. Yeah, let's. Okay, great. This A and B is A is Alice's vector and B is Bob's vector. Great. This MP is the map, the DP what we are using. This P is our pref vector. Initially, the we assume that the first one is at index minus one, right? So this entire block helps us calculate the number of elements or number of ranges LNR where we don't watch any episodes. How we calculate it? For every index, we found out the last P. This PI is the last one's location. So I minus PI gives us all the elements where one does not exist, right? And also we have to make sure that this element one does not exist. So this is how we are calculating initial number of elements, right? I hope this was clear. This is where when we had no ones. That means let's say 1, 3, 4, 5, and 6 and 7. This PI for this index will tell us it's at index 0, right? And to calculate number of endings where this R was used, we will calculating all subarrays that we could for sorry, 1 second. Basically, all the subarrays well for LNR where R is the ending at the index I, right? So this would 1 and then 2 here. And similarly, this gives us the answer for the first part. Now, this is not a beautiful code, but yeah, let's see. If both are equal and equal to 1, that means we have to calculate something. What we have to calculate? This x is our A or the this x is actually B, the number of elements we had. This this B is our x in our code, and this A, I think this add. I don't know why I have. This is just a variable, right? Just map it. This x, and we are just multiplying it. You can already see instead of vector I'm using map, but you can know that the number of elements for each element it exists from 1 to n, so you can use a vector too. It's super cool. If both are equal, then AI would be equal to AI plus 1, right? This cost me the wrong answer. Otherwise, if no elements greater than it exists, we are going to place it as n. And then finally, if both elements are not equal, that means AI is not equal to BI, we are going to place it like it. That means this would be the end of chain. Again, you must have noticed something. Here I'm actually storing I plus 1 or like elements. This tells us that the code I gave you or the logic I gave you, we calculated till the element it was valid. It calculated till the element it was valid plus 1 in the code, right? Till the element it was valid plus 1. Great. So this is how we calculated the MP, which is our DP actually. And then we printed a final answer, right? Yeah, this was actually a good question. Too much to explain actually. Not a one shot, but yeah, just notice this part first that we let's assume no episode watched and at least one episode. If no episode watched, how can we calculate it? If at least one episode, how can we calculate it? Sure. I hope so. This is super cool. Thanks a lot, dude. Thanks a lot. It really keeps her like it really motivates us. Do like and subscribe, dude. Thanks a lot. Now let's go towards the fifth problem, the minimum influence problem. Imagine that you are an owner. Anyways, any of you folks have any question? I'll wait for like 20-30 seconds. Let's move forward. Yeah. So the question number E, minimum influence. Okay. Imagine that you are owner of a news website and want to study how some selected news item affect your users. You have n news items. For each item, you have to determine two parameters. You determine two parameters, how it touches politics, PI, and how it touches culture, CI. Got it? So here, the first point, you have n news items, right? Each item, each item has two parameters, PI, which is the politics parameter, and CI, which is the culture parameter. You have M users whose reaction to the news is you want to study. For each person, you have determined three parameters: tolerance to political news, tolerance to cultural news, and zero influence of uh, and the zone of influence. The influence politics IP and the culture IC in the news item I on the user J can be calculated using this formula, right? In other words, while amount of politics is P, this is just explaining this formula. We're going to study it. We're going to basically expand and see what does this formula do. The total influence of news item I on J is IJ. IP, this is the influence of politics, and IC is the influence of culture. For each user J, determine the minimum influence IJ, comma, among all the news items I. Super cool. Let's see. Basically, what we have is this is each item. We have few persons. We have M persons, M person, right? And each person has three parameters. One is TP, one is TC, and one is D. This is like, uh, 1 second. Yeah. So this is tolerance to politics, tolerance to culture, and tolerance. And this is zone of, I think, what's this called? Yeah, zone of influence. Yeah, this T, right? For each person, we have these three parameters. And then we have this formula, which is for influence of politics and influence of culture. We basically want to study how the news are going to affect persons. So for that, we have one formula. Influence of politics. Influence of politics is equal to three values, either zero, either, I think, PJ, PI, yeah, sorry, PI or TPJ. Note something here. This I is a item, news item, right? And this J is nothing but user. We know that there are M persons, this M person or this M users, and this N items. So I tells us about an item, J tells us about the user, right? So basically, this IP is influence of politics, and this IP I comma J tells us influence of I comma J. This tells us influence of politics on user J by item I. By item I. By ith item, how much influence will it take? So it has two parts. This is influence of politics, this is influence of culture. Both will have the same, like, sort of a same formula. So this could be either equal to zero when the influence of politics, TPJ, is greater than, oh, sorry, I forgot, right? This is, yeah, this. I was right actually. TPJ, here also TPJ is greater than PI. I is the news item, by the way. Similarly here, if PI is greater than equal to TPJ, but less than TPJ plus D. These are zone of influence, DI basically. And here if PI is greater than TP or equal to TPJ plus DJ actually. J is our user, right? This. So this is a formula that we have. Similarly, the influence of culture of item I on person J is equal to three parts again. 0 and this is not P, right? This would be C. CI, TP, sorry, TCJ. So this would be equal to, again, just map it out. TCJ, sorry, TCJ is greater than CI. CI is greater than TCJ, greater than equal to 8, but less than equal to TCJ plus DJ. And if CI is greater than equal to TCJ plus DJ, right? So this is the formula we have. And including these both comes our value IC, I comma J. Or I, capital I, not IC actually. Where just IC was cultural influence, right? This IC is equal to IP, I comma J plus IC, I comma J, right? Yep. This is the formula that we have, right? So we want for each user, for each user J, we want its least value. Also, the constraints are like normally like what we have for any code process problem, that n is less than equal to 2 into 10 raised to power 5 and m is less than equal to 4 into 10 raised to power 5, right? So yeah, typical constraints. Now let's see how are we going to solve this. This I comma J for capital I. This is what we need. We want this its value to be as least as possible for every user J, right? So how can we calculate it? To calculate it, let's actually we have to understand it mathematically, right? What I took this, what I saw was we have two terms here, right? Which is, let's expand it. IP, which is influence of politics, I comma J, plus influence of culture, I comma J, right? We have these two values, right? And we want both of these values to be as less as possible. There is one thing you must notice, that for this, we have three possible outcomes or three possible values that this value could have. This could be either be 0, either this could be Pj, or either this could be TPJ, sorry, Pi actually, Pi and TPJ. These three values it could have, right? And similarly, even this could have three values: 0, Pi, sorry, Ci here. I is again the news item, J is the user, and TCJ. These three values, right? So how can we calculate it, right? What we could do to calculate it? So, so, can we map it out? For example, can we take an example like what I thought was we had three values for it and three values for it. That means at max we could have 9 possible variations. So I thought, can I check it? Can I check it? Right. First variation net, I got 0 value here. When would I have 0 value here? I would have 0 value here when P, sorry, yeah. Pi is less than TPJ. I already know this value, right? There is one thing that we must have noticed that we have to find for each user, right? For each user, we have to find out. That means we will, let's say we are iterating on each user, iterating on each user. When we iterate on each user, we will have three values. This is what we already have. This is TPJ, TCJ, and DJ. This values we already have, right? Because we are iterating on each user. Now, what I wanted to like find here is we can have three possible values for it, right? I thought, let's say, if zero was here, that means Pi was less than TPJ. Okay, great. And like there would be certain values where Pi would be less than, let's say Pi was sorted and we had values like this, P2 and P3 dot dot dot, and then we have C0, C1, C2, and C3. And this array is sorted by it, sorted by P, by P, right? For some Pi, this array, for example, this array, for example, would be, let's assume that P2 is less than TPJ. This I can easily calculate, right? Let's say if we have this two vectors, right? Initially, we would have all items umble jumbled, but we can sort it out, right? What if we sort it out? Then I can easily find what element or what index would be the maximum index where this TPI would be less than TPJ, right? Such that when this occurs, then for this TPI, we would get the answer equal to zero, right? Because this PI is less than TPJ, right? Now, this for this index, we want the least value. That means we want the least value out of this least value, right? To find the least value out of this prefix, least value out of prefix, this can easily be calculated using some prefix array. You got it. You got it. You got something right. I said, I said we have nine possible combinations. Either we would have zero here or some of zero CI or TCJ here, right? Either we would have PI here and some of it here, either a TPJ here or any of it here, right? So nine possible variations. So I'm saying when I iterate on each user, what if I just check all these nine patterns? The first pattern is this. What if I had zero here? If I had zero here, first, let's say I would like, let's say I had this. This is our items array. Items one. I have two items array. Items one where it's sorted on basis of P. Sorted on P. Why sorted on P? So I can calculate. We have to find this index, right? Pi. This index Pi. I calculate. I said, let's say this is the last index. How can I find this last index? I can easily find it using lower bound. Uh, while I was coding this, I used segment trees too, and like lower bound is nothing but binary search or finding last element, which is finding any element which is greater than equal to our element that we want our value, right? So this tells us the first element. Lower bound is nothing but this is a function that is used in C++. Either way, you can use binary search too, right? This in logarithmic time complexity tells us the element or the index where the element is greater than or equal to our element x. Lower bound on x gives us this. So in this array, on this like what this array, we can do lower bound and find this p2 or find this index. Then till this index, I could calculate the minimum value of c where we could get. Because for all the elements, this, or this, we would get zero here, right? Zero for IP influence, right? For all the elements because these are sorted. That means they are this range. So if this is less, then all the elements will be less. So I can take any element. So I choose the element with the least value of C. How to choose it? I'll keep a prefix array. I can also use segment tree. I use segment tree personally. because I was like just coding and coding and I had little time left. Upsolved it basically. After like uh, after 1 or 2 minutes of the contest, I completed my code and then yeah, I was late, so I couldn't submit it during the contest. But yeah, anyways, so I use segment. You can use segment tree to find for this segment what is the least value. So we will choose that element with the least value. Let's say C1 is the least, right? So we'll choose this. How we can easily calculate using prefix arrow or something, right? And use this C1 here. Now for this to calculate IC, we have C1, the element we have, like any element like C1 is basically the least value we could get when we have 0. So we calculated for one variation where IP was equal to 0. We would calculate this IC using this C1. We'll put this C1 and using this, if this C1 is less than TCI, TCJ, sorry, then we will get 0. If this C1 is again greater than equal to TCJ and less than TCJ, plus T. Again, this TCJ is known, this D is known to us, right? So we can easily calculate it. This would give us CJ, C1, sorry. No, so, oh yeah, C1. And if this C1 is greater than TCJ greater than equal to plus T, we will get TJ, sorry, TCJ. We will, using this C1 that we calculated from here, right? We would get the value of IC. So for all IP0, we will get this value, and this is our first possible variation that we could get, right? We can easily calculate it this way, right? Now the second possible. So we use this when we have use 0 here, we can easily calculate it for here. Now similarly for TPJ, yeah, we are going like we'll study this later, right? Let's say when we have to choose this, let's say that means IP has TPJ. We are checking for all possible line variations, right? If we choose this, now we have to check like instead of checking for all the possible values, let's check for the best value. So how will you get the best value? What we did for 0, I calculated the best value of C we could get, or the least value of we get, because least the value, least its value would be, right? These are on decreasing order, right? Ci is greater and this is greater. Anyways, so least the value we get, the least value we will get for these functions. And for these functions, because finally we want the final least possible influence, right? So the political influence we choose, let's say the political influence is 0, then what is the least value of C we could get? And then we applied it here and we solve this, right? That means if we choose 0 here, we know the best possible answer. What if we choose this? We went all out. That means we can choose the entire array, right? Second case, second case, when IP is equal to PPJ, which is max. That means PI or any like element we had. This was P. Yeah, PI is greater than or equal to PPJ plus D. Or this is X max X possible, maximum element basically. That means let's say for this array Pn, this was again sorted order C0, C1. Again note that P this array is sorted. This is not sorted. Again, if we like we can take any element now, right? We can also take this, or we can take now all elements are accessible to us. So we will take the least value of this, least value of this. Yeah, we will take that, and using this we'll put this in TC function, or sorry, IC function to find this, because we got this C2. Now we can easily put this in function and get either 0 or CJ or CI, sorry, or TCJ, right? And we've also calculated for this case where we had the maximum influence. Can we go the vice versa too, right? Similarly, as we build this array, we can also build this array. C naught, where this is greater than C1, this is greater than equal to C2, and this is greater than equal to dot 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 Cn, right? And here these are now randomly aligned, random sorted, greater than equal to P1, greater than equal to P2, dot 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 Pn. That's next month's. I have my internship test next month and still can't do 400, 1400 to 1500 problems. What to do and how to improvise? I would say whatever your rating is to plus 200 and like start from there and go build brick by brick and like solve 10 problems a day or something like that and then try to improvise it. Like you have next month, so you have 30 days, right? If you solve 10 problems a day, like till you get comfortable after I think 40, 50, you will get comfortable, move towards the higher rating. I think this would help. Like, I hope it does. Anyways, back to problem. Yeah, for this, let's say this is sorted and this is not. Now, again, we can calculate two cases for IC. For IC, I comma J. One case when we had 0 and one case when we had, again, we had 0. That means the CI is less than T Cij, right? So I can again do binary search, calculate the index till the where, let's say if C2 was less than equal to our Tj, our current Tj, then I can again find the minimum of it. The same thing that we applied here, right? And then I can use that value, right? Let's say we got P2, this was the minimum value. Apply this to a function IP and get some value out of it, right? And use this value. Similarly, it goes same for the TCJ actually. Let's say if the value was TCJ, this is same like thing that we did here. TCJ, that means we have the entire array. So we will to pmin, will apply it to our IP function I comma j, and we'll see what value we got. Let's say we got y. So this would be equal to y plus TCJ, right? And we'll check if this is minimum or not. Right. So basically we'll check for all 9 variations. So I checked where what if this is 0 and we have some value here, best possible value here. If this is this and we have best possible value here. Similarly, this is 0 here and best possible value here. This is this here and best possible value here. So we check for all these cases. What is the case that's left? Right. There is the only case that's left is PI. When these we use PI here and CI here. Right. So what happens where we have PI here and CI here? So what I did was this observation that you have to do is take this MN. MN is minimum of all PI plus CI, right? This MN will solve this problem for all the like problems, right? Why? Like why? Because let's assume this PI and CI, this would only occur when we would only make this case when pi is less than equal to pi plus tpj plus t, and ci is less than equal to tpj plus t. I would say the minimum value of pi plus ci would always work. Why? Like what if this minimum value is too great, too large, right? There might be a case when pi is equal to like 1 and ci is too large. Let's say it's L goes for large, right? Then it might have already occurred or already covered in these cases, right? Where uh, if this is it, right? I'm saying that calculate the minimum of pi and ci for all the values, right? And let this value be mn, right? And this mn is universally true for all users, for all users, right? But we know that this mn will only be true when pi would be less than tpj plus d, and ci would be like it depends on j, right? You would like raise this question, but I would say that, right? I can make this argument, right? That This is globally true for all. Globally true. Globally true. Why? Right? Why? Be- One second. Just one second. Yeah. Because let's assume that this value pi was greater than this value, right? If it's greater than this value, greater than equal to sorry, this is not equal to, again, this is just less. Tpj plus d is greater than equal to d, then it does not lies into this set. Then we are checking this, and we have already checked this, right? Similarly, for all the cases, you can see if we are getting this pi and ci, we might as well use this value. Otherwise, all the other cases already checks it, right? That means for this, we can take a global mn value and check if our answer is minimum of answer comma this mn value, right? If this mn value doesn't lie into our answer, that that might be a valid argument why are we using this global value, right? Then it would like basically this mn, there would be a better value that we could get from here or here, right? For example, if this pi is too large, right, you can say that if pi is too large than this, then what value are we using? For ip, we will use tp, uh, sorry, tpj, right? We will use this tpj, and this tpj would be less than pi. That means there exists a better value. This is a better value, right? Better value. That means we wouldn't have to consider this value in the first place. That this would be disregarded, right? So don't worry about this value, right? Basically, this is little glitchy. Yeah, right. So this is how we did it. We basically calculated all the possible scenarios, right? Let me actually dry run it and show you how we did it using some example. This would work. A quick dry run. Yeah, here we go. Now we know we need two values, first sorted on these values and second sorted on these values. Let's take it. If we sort on first values, this would be like 1, 2, 4, 0, 6, and 10. This is sorted on political value, or like the political influence value. And this 0 is mapped to 9, 1 is mapped to 6, and 10 is mapped to 0. Similarly, let's sort on basis of the cultural value. So this would result in 1, sorry, 0, 1, 2, 3, 6, and 9. This would give us 10, 6, 4, 2, 1, and 0. So we have like four vectors basically, or whatever, right? You can sort on this and then this and whatever you want, however you want to sort. This is sorted on C. Let's say we reach the first person. This is a first person, by the way. 0, 0, 9. This is TPI, TPJ, sorry. The person is J always. This TCJ and this is T. Right. Now we have three values that we need to check. We will check for this and we'll check for some this number, right? The numbers are like, how are we going to check it? We know that this would be equal to IP plus IC. This capital I that we need to check. The possible values of IP is 0, PI, TPJ. Let's check for 0 first. And similarly for this, we have 0, CI, TCJ. Let's check for 0 first. If we have 0 here, right, we will have 0 here when PI is less than TPJ. The TPJ here is 0. How many values in this sorted order is less than 0? None. None. That means Any case does not exist where IP, this is value 0. Okay, great. Now let's, this PI and CI can easily be calculated using the minimum of all these, the sum of these. The minimum of all sum of these is this 5, right? So we'll make it 5. Okay, here we got 5. What if we took TPJ? This TPJ will occur when PI is greater than TPJ plus T or whatever values basically, right? So we can take any value here, any value here. Okay, great. What is the least value we can get? We get C equal to 0. This 0. Got it. What if we applied this 0 here, that we have 0 here? What IC would get? IC tells us that IC tells us that either we would get 0 if whatever C you are giving, this CI is less than TCJ. Either we would get CJ if this CJ is greater than equal to TCJ, but this CI, sorry, is less than TCJ plus T. Otherwise, this would be CI plus T. Sorry, TCJ. When it's CI is greater than TCJ plus TJ. Got it. Here you can see TCJ is equal to 0 and CJ is also equal to 0. This is 0 that we have, right? CI basically. Our CI is equal to 0. So 0 is less than 0. Okay, great. This condition will follow basically, and we will get 0 as our answer, right? So IC is equal to 0 and IP is equal to this TPJ. TPJ here is for this value equal to 0. These both are 0, right? This would be equal to 0 plus 0. Both are 0, so answer would be 0. Am I doing something wrong? Right? This answer is 5. Oh, sorry. Yeah, just 1 second. 1 second. Oh, sorry. Oh, this part we forgot. This TPJ plus DJ. Really sorry, I thought so, right? But this doesn't make any difference that the DJ plus DJ. Everywhere just follow this part. I'm really sorry, I forgot this part. Plus DJ. The rest, like, just make note of it. The TPJ was DJ. This would become 0 plus 9 and 0 plus 9. This would become 18. But here, our initial answer was 5. 5 is less than 18. So kudos, we got our answer. Our answer is equal to 5. Right. But basically, I thought you got the flow right. We will make these two. We'll use this to find like all the possible permutation. Similarly for here too. What if Cj is equal to IC is equal to 0? Again, we will do a binary search here. Again, the no elements are equal, so we'll basically quit. But what if we have all the elements? Then we'll take the least possible value, which is 0. And then we'll apply this 0 as pi equal to 0, and then we'll apply it to IP. And IP's value is again either 0, either TPI, TPJ plus DJ. I'm really sorry I forgot this part. I think I'm a little sleepy, but yeah. And this is TJ. Yeah, according to conditions. Right. And again, this 0 would lie here, and this would again give us 0. But the problem is this 9, which will cause us problem, this DJ, which is equal to 9. Yeah. Right? So this would be again one more thing. This where we calculated IP, this IC would be equal to this value would be 9 actually, right? Because this where when we chose this, we got here, right? And this was equal to 0. So we got 9 plus 0, which is equal to 9. But as we are doing minimum with 5, this would be our answer. Similarly, we calculate for all different possible cases, right? So basically we make this array and then we calculate it. I hope this is crystal clear now. Let's actually see the code. Right. The code is little cluttered, but yeah, this part basically does the two array making thing. This is just a segment tree that we are using instead of like prefix array. We can use both. This is again what we do the like find the index. If index is not equal to 0, we query using the segment tree. This is the first part where the initial that 0 we got on the left side. Similarly, here we are doing the opposite for the cultural influence, right? This is the political influence, this is the cultural influence. And initially what we set as answer equal to MNS, the value we calculated, right? And this is like finally we'll print this. I hope this is crystal clear, right? So basic funda is same. What I like showed you that we basically find the minimum on both sides. We sort it on basis of political influence, and then we find the minimum value, and we sort it basic of on cultural influence, then we find the minimum value, and then the total minimum value on the both sides. So yeah, that works, I guess. Right. And this MNS, I hope the logic behind it is clear. MNS is what? It is minimum of all values of AI plus BI, where AI is some like item, news item. What I wanted to say from here is either this would minimum, either we would do it using some other case. Why? There might be a case where AI is less. When we will get AI on left side, what does this mean? Right. Here the answer was 5 initially, right? What does this mean? This means that IP gives us PI and IC also gives us CI. When we will get it? We will get it when this PI is somewhat less than equal less than TPJ plus TJ. And similarly, this is also less than TCJ plus DJ. Right? These two has to be less than it. Right? Also, this has to be greater than equal to TPJ. Notice something. If this is 0, if this lies here, if this is its value is less than it, right? That means we are finally covering this case. What case? The first case, which was where we take 0 here and then the best possible value here, right? That means it's already covered. If we are taking somewhere value which is greater than it, greater than equal to it, then also it's already covered because this case is a separate case when we got TPJ plus DJ here, which is this case. Then we choose the best possible value for it for IC, and then we put it and we get the answer, right? So both cases are already covered. That means if I choose this any MNS, right, with the minimum of PI plus CI, PI plus CI, either a better value exists, right? As you can see, if like PI is less than it, then no, like we should not choose this value, right? But if it's 0 or less, if it's 0, then we have already calculated the best value when IP is equal to 0. Similarly for this case too, right? And similarly this value, if it's greater, then we have already calculated the best value when this is greater than it, right? So we have already calculated those values. So this would be either better value might exist, either this would be the best value. That's why like we are chill and we are using MNS here, right? It's pretty late, so yeah, let's end it. If you folks have any doubt, you can actually ping me out in the comment section. I'll end it in 30 seconds. If you want to, guys want to ask something, you can always ask. Okay, let's end the stream, I guess. So yeah, bye folks. Good night.